Annemarie Baltay, and I think she's probably well known to most of you here. Her background, she's with the US Geological Survey, and her background is in earthquake ground motions, both from the point of view of simplified physics models to explain them and observational ground motions. I think a lot of you are probably familiar with the work that she's been doing, leading a very interesting project on trying to make less ambiguous, a very ambiguous source parameter known as stress drop. And today she's going to give us her perspectives on kind of the interface and some observations that speak to both earthquake source physics and ground motion modeling. Take it away, Annemarie.
All right, thanks, Gail. Thanks so much, everyone, for organizing and being here and for the invitation. Yeah, so as Gail said, I'm going to give you some observations. So switching from, Elise was talking a lot about simulations at the intersection of ground motion and earthquake physics. So I think perhaps it's obvious to everyone here that we want to catch the big one, and I could have given examples from trying to catch the big one at near source. Maybe Gail will talk a little bit about that also. And Bill's going to talk about that. So I'm going to try to convince you here that there's a lot of other things we can do with this near source and dense data, and particularly some examples from small earthquakes, because I think while we're waiting for the big one, we have this array out, we want to catch small earthquakes. That's the data. Oh, there we go. All right. Oh, which way did that go?
The down button.
I think it's the down button. It's a little, yeah. Okay. So just before we started, just to make sure everyone's on the same page, some people are really familiar with this notation, other people are not. I'm going to be talking a lot about different components of the ground motion. So the observed ground motion at a station from event I at station J can be considered the median ground motion model, and then the residual. And we'll focus a lot about the residual component, assuming that the ground motion models are pretty fit and unbiased. So the residual can be broken down into the component, the bias, and then the event term that's dependent on the event, the site terms are dependent on the site J, and then the path term that's dependent on both of those. And here I'll show some examples where we've identified, or we are attempting to identify the repeatable components of the event, site, and path. And just to get you oriented here, there's two different color bars, just depending on who made the figures, right? This Viridis one, where the yellow is going to be larger ground motions, and the navy will be the smaller ground motions, and then the more common perhaps in ground motion modeling, the red blue color bar. So the red and the yellow are large ground motions, blue are small. Let's see. So first, okay, here's an example from observed PGV ground motions at the Sagebrush Flats array. So Sagebrush Flats is an incredibly dense array. The whole array takes up about 0.6 by 0.6 kilometers with 1,000 or 1,100 geophones, 10-meter spacing. And it was deployed for about a month. So we can immediately see here, this is the repeatable site component that we can identify these really small scale basins, right? This is 600 meters. So this is a very small basin here next to some of the faults. So using these really dense networks, we can sort of see really small scale site effects. And this again, so I'll highlight here whenever there's small magnitude data involved. This is only from events magnitude 2 to 4. So we can harness this small magnitudes reported on this dense data to identify these basins and site effects. And then on the right here, so this is the repeatable component and the variability there. On the right are just two specific examples from magnitude 2 earthquakes, one coming from the north into the array, one coming from the south. And again, you can see really similar repeatable effects here in this small magnitude data. So perhaps very similar to that Sagebrush Flats array is some work at LASO. This is not my work, but this is a recent paper that just came out, I think, a week ago, so check it out. Again, similar, but a little bit larger spacing here for the LASO array, about 40 kilometers by 20 kilometers with 400 meter spacing, and some regional events between magnitude 3 and 3.7. And here we see, so the previous example was kind of just observationally, totally empirical. We saw some side effects. Here, they're proposing that the observed side effects can correlate, or the observed effects correlate either with the far field radiation. So this is the P waves coming across the array, again with the yellow being the large ground motions and the purple being the smaller ground motions. And they look visually really similar to this far field radiation pattern for P. And then for the higher frequencies for both the P and the S at 10 to 20 hertz here, we see these patterns more where the larger ground motions are sort of in this region. Here, it's really difficult to see, I think, but this is a map of the geology overlaid with one of these patterns, and you can see that there's shallow alluvial sediments in these kind of light tan colors that they're proposing are contributing to higher ground motion. So shallow geology affecting the high frequency ground motion. So here's an example of how we can use geology, in a location where we maybe don't know the seismicity, or we don't have as much seismicity in Oklahoma to predict the ground motion. So this is a really appealing idea, using other information to help us inform the ground motion models. And again, this is small magnitude data. Moving back sort of to California here, this is an example from the Anza region, again, earthquakes of magnitude 1 to 4. And we were curious here, can we look at the path residuals and correlate that with some existing velocity or attenuation or geology structure? So this is our data set on the left here. We looked at a small magnitude ground motion model and calculated the path components, so decomposed the residuals into the path components. On the right here, there's clusters and stations from the Anza network that are crossing the fault here, and each colored path is showing the ground motion path residual overlaid on a velocity model. So our question was, can we simply take these two discrete data sets and correlate them? Can we take the ground motion path residuals based only on the velocity model? And again, another example of where we could have a physically based, informed, non-ergodic ground motion model to other regions if we find this correlation. So Valerie Sahakian did this work, taking that idea. So she took a much larger data set there and considered this velocity model from Banganal for S waves. So from that ground motion model that she built, she calculated the path residuals, and then separately for every event station pair, ray traced through the velocity model and calculated this path integral of the velocity gradient, and found that those observed path residuals correlate with the path integral of the velocity gradient from the independent velocity model. So here's an example of that velocity model gradient on the x-axis, and then the observed path term on the y, and there's a correlation here to say that when there's a larger path term, that's when we saw a smaller velocity gradient, and when the velocity gradient increases, we decrease the path term. So we're getting more attenuation as we increase this velocity gradient. So as we travel through more velocity contrasts. And here's just an example of the ray tracing, and you can sort of see some of the variability here at a particular station where we have much higher ground motions coming from one side of the model as from the other. And I will just say, this is, if you read this carefully, this is at very longer distances, but we think that's just due to the resolution of the model. We tested this with an attenuation, a Q model, and found that the resolution was just insufficient. The Q blocks were just too large to be able to see this kind of detail. So we do need finer resolution on all of these models in order to continue this work. And there's also, we found no magnitude dependence in this. So this is looking at small magnitude data, but we found no magnitude dependence. So we think these kind of relations could be extrapolated up to much larger magnitude. So again, harnessing the small magnitude data here. This is an example from the South Napa earthquake, so magnitude 6 earthquake occurring here. And now we have the red-blue plot where the red is the larger ground motions, blue are the smaller ground motions just from this particular earthquake. And we see a lot of features here. There's maybe a basin up here in Santa Rosa, but if you look to the south here along the Franklin and Southampton faults, seems like there's ground motion amplification. So the question was, are there fault guided waves? At this scale, I think it's really hard to say what's going on, right? So obviously, I think if we had denser arrays, we could sort of look at this in more detail. So Rufus Catchings et al. Went out after the South Napa earthquake and deployed 3 arrays, very similar to the proposed RuFZO layout. I'm just going to talk about this one because I think that's the most interesting for what I was looking at. They did indeed see increased amplification here. I think that's perhaps almost less surprising because we're pretty sure that there's some connectivity there, but the question of whether this connectivity here, I think, is pretty interesting. So here's 2 examples from a magnitude 1.3 and a magnitude 1.2 earthquake that they caught with these nodes So let's see, they had about 10 to 20 nodes across each of these small arrays, and they deployed them for only 10 days. So pretty small scale experiment here compared to what RuFZO is proposing. And you can see here's where the trace the Franklin fault comes in. This is PGV from that one earthquake, and the Southampton fault here. And again, the Franklin fault, Southampton for the other earthquake. So I think there's definitely hints of seeing increased PGV as you cross the fault there. So implying some sort of perhaps fault guided or fault trapped waves. But at this kind of station spacing, I think it's still difficult to really discern whether that's the case. So obviously, and even in their paper, they suggested that a longer, denser, longer time array would be able to get these questions better. But again, using the small magnitude data to sort of inform our understanding of what could happen for the larger event. Another example from NAPA, now sort of going from path into source. And this is the recordings of PGA versus distance for the South Napa event. And we have a few close source data that are highlighted. But you can also see that there's large attenuation as you move away from the event. So the question of, in a ground motion sense, whether this was a normal stress drop event, which is how I interpret it, or if you just fit all the data, if it's a lower stress drop event. Perhaps it seems obvious to this crowd, but when you're decomposing these ground motion residuals, there is a huge trade-off in how you fit these data and how you then interpret the source physics of the earthquake. So doing various tests with the NGOS data, you can see that there is a correlation here in that if you, there's a trade-off between the event component here and either the geometrical spreading component of the path or the Q component of the path here. So if you are incorrectly identifying your near source data, you're not going to get the right understanding of how the attenuation works. So again, just emphasizing that we need that near source data for ground motion modeling. And I was really excited that Elise was showing Parkfield. Maybe it's having a comeback for some of us who missed it, perhaps. But, so this is where Grace Parker will show at this meeting, so you can check this out in more detail. But here's again, red for large ground motion, blue for small ground motion, observations from the main shock for PGV. And you can see again, we have these, kind of similar sort of fault crossing arrays here. The method she's working on here is to take some empirical Green's function events, which could happen before or after any time that we can get the data, and define the repeatable site components, and then remove those site components. So now we're really isolating. Here we're interested in the directivity of the main shock. So I think it started here and probably propagated to the north, but did it also propagate to the south? But the smaller events aren't as well recorded. So when we remove the site effect in the small events, we can only do it at the stations where the small events were consistently recorded, and it actually just reduces the total number of stations that we have in the data set. It's a little bit hard to see with all these tags on the station names, but we just don't have the density when we do this method. But when we do adjust it, we get a much clearer picture, we think, of the repeatable, or removing the repeatable components to get at the directivity. But again, if we had the smaller magnitude data recorded more consistently closer to the fault, I think we'd get a much better, clearer picture of the propagation here. So check out Grace's poster for more details there. Similarly, looking at the source component for the Ridgecrest data. These are the event terms. It's a little grainy here. Event terms for the aftershock magnitude 4.5 or larger for PGA and for 5 seconds, colored by the amplitude of the event terms. And so we wanted to ask, so red are large event terms or high stress drop events, and blue smaller. Is there a pattern with what we're seeing here compared to what happened from the main shock or the magnitude 6.4? But at this resolution, it's still really, I think, difficult to see what kind of patterns, if any, we're seeing here. So if we had, better understanding of the near fault ground motions or the rupture. So here's just looking at the cross section for the same data, and I just put some rough contours from the initial conversion from Gavin Hayes. All the data is in gray, and then the colored dots are again showing the PGA and the 5-second PSA event terms, so the same as before. So having a better understanding of what happened during the main shock would be useful here, right? To understand what happened during the rupture, and then also just getting better resolution on what's going on here. So we're also trying to answer these kinds of questions with our stress drop validation group that Gail mentioned. So here's just a little plug for that. And this is poster 29, you can check that out too. And obviously we're using not obviously, but we are using a lot of small magnitude data. We distributed data down to magnitude 1. We're not really looking at the magnitude 1s, but maybe 2 or 2.5. And this is just a really rough projection of all the data we've collected so far from everyone who's contributed. A lot of people in this room have contributed, so thank you. And this is just the average stress drop projected onto the main shock fault plane, which is obviously a huge approximation, but just rotated in that direction. And then the question is, can we start to see patterns in stress drop? We can sort of see here, yellow is the higher stress drop and blue is the lower stress drop. Maybe there's depth dependence, we can account for that, but are there along strike variations in the stress drop? So these are questions we hope to answer a little more detail with the stress drop study. Zooming in on one particular event, this is from Shanna Chu's poster. Again, you can check that out in the next few days, poster 25. This is looking at one magnitude 3.5 event occurred here along the main shock fault plane, recorded on these stations, and she's looking at how the corner frequency and the spectral ratios vary around this event. So is there directivity? And it seems like we can see that she's fitting directivity pulse to these stations. So this is really interesting work, but obviously I think it would be improved if we had more near source stations here to constrain that, and particularly for the directivity to understand what's happening for these smaller events. But here again, an example, we can harness the information of the small events. This is my last example. So this is another way of looking at stress drop. This is from the NGA West 2 database. This is looking at the RAS intensity. And here we can see with distance, this is the stress drop on the y-axis and distance on the x, colored by the earthquake magnitude, that we have all kinds of interesting patterns occurring here. But particularly we're just have very few close-in records of all the events and of the small magnitude events. So to really understand what's happening here. So we think that for the larger events, the yellow ones, the magnitude 7s, we're out to about 200 kilometers. We don't see any attenuation here. We do see attenuation for the smaller events. And on the near source side, we're actually just seeing a reduced observation window of these large events as they zoom by at these high frequencies. But really understanding that would be interesting to see how those ruptures are going by. We need to fill in some of these data. And looking at this same data set, asking the question related to the previous question I posed, kind of is like, what are these aftershocks doing as compared to the main shock fault plane? And then also, how far on or off fault are they? And can we define, any kind of main shock rupture width? Or I don't even want to use words like the outer zone because that's out of my wheelhouse. But it's a really interesting question that we can try to answer looking at the energetics of the other events. So on this plot on the right here, this is the magnitude of the aftershocks. And so these are details about how we defined aftershocks and main shocks, but that's, I think, less important to the point I wanted to make. But here's the distance from the main shock fault plane, and then the stress drop from those aftershocks. And so maybe you can see in this data set here that events that are on fault have sort of relatively higher stress drops. The stress drops drop as you move off fault, and then they recover to some sort of background rate. But you can see here, there's still really not that much data on this plot. So understanding where that fault plane is or isn't from other work, and then getting the near source data here. And again, this is, you can use small magnitude data here to define what's happening. All right, then I just want to quickly mention this, a little different than what I've talked about, but on the RuFZO plot, there are some DAS lines there. And so this is just some quick example of what, I think we can do with DAS for ground motion. This is actually looking at strain meters, but we can, DAS is strain. These are for 9 earthquakes around California, again, of moderate to larger size, magnitude 4.4 here up to 7.1. And the red data are the strain meter PGV, so strain converted to PGV, and the seismometers are all in the background. And basically, I just want to point out that using these strain meters to PGV gives you ground motion data that is totally comparable to what we get from seismometers. So I think we could, use these DAS to constrain near fault ground motions. So there was a lot of different examples, but hopefully I made the point that we can do interesting science with near source and dense small magnitude data while we're waiting for the big one. And that observations of small earthquakes can inform both the physics and the statistics for larger events. So we can do both statistically based ground motion modeling and sort of this physically based non-organic ground motion, where we can then extrapolate to regions where we have less seismicity, with implications for both earthquake physics, for understanding earthquake physics, and for hazard for ground motion modeling. So small earthquakes and small ground motions are, I think, super interesting. Thank you.
Okay, thanks, Annemarie. We've got time for a few questions for Annemarie. Once again, does anybody who's up, you want to go ahead?
Just, I mean, that's great. Some of the interesting problems. I'm just curious, what about the benefits of a near surface versus borehole? If you can get below the near surface, does that help these problems, or?
I think so. Yeah, sure. Because
but it's expensive. I mean, is it worth it?
Well, I don't know. That's you gotta decide.
Yeah.
Yeah, no, it's totally worth it, right? So, in Japan, right, we have the surface and the borehole, and then we can better constrain the side effect of the surface, right? That's where a lot of those side effects are coming into play that sort of confuse what we can observe, right? So we can get rid of those. Like the problem I pointed out in the beginning is trying to separate these components. So depending on what you're curious about, if you're curious about the source, you want to get rid of the side effects. So having the borehole, sure, will definitely reduce side effects. Yeah. And there's in the Chris Johnson paper from Sagebrush class, there is one borehole that he looked at, and I think there's data he showed in that paper.
Very interesting thoughts. So to follow up on this question, right? One could imagine that side effects would be larger, or maybe more unpredictable, closer to the fault, right? Where there's like damage zone, lava structure. I'm just wondering whether anybody has looked into that or not. Like systematically. I mean,
yeah,
there's amplification of motion, right? But
right. I think it's still difficult to. Oops, I'm just going to show the Sagebrush class example. It's still really difficult to say because we have so few observations really, really close. But it seems like there's some sort of fault dependent structure if you squint your eyes at some of these, right? So, and this is the variability of that. So where the blue is the lower variability. So where you see the blue, it actually means that we think this is more repeatable, so more consistent. So I don't know, maybe the opposite of what you're proposing or not. I think these are still.
I was asking.
Yeah. It seems like it's more repeatable, and I don't know, is that depending on this particular fault structure or? Yeah.
It depends on, I think, on the fact that there is pre-existing structure that puts a signature and it's repeatable.
Yeah.
And you see it even in the noise. And there is a board.
Yeah, there's a board in here. I just forget.
Here and there when we can hear, there is a board.
Yeah. So in this paper that Chris wrote, there's some. This is just one example. There's some great stuff in there. Yeah.
But was curious to kind of follow up on that, the role of the geology, the shallow geology, and for the RuFZO, it seems like it's a little bit circular. Like it'd be useful to know the geology at high resolution before or as part of the network design, but also once there's events and a dense network, it could refine the shallow 3D structure. So that's really interesting. And I think it does the other science point is just, how does the rupture at depth interact with that upper kilometer of geology? And I think it's quite challenging to anticipate, but that could be a great opportunity for sort of linking the observations.
Yeah. So probably people here know more about this geology in Oklahoma, but this is very shallow, right? I think a lot of this is superficial geology. So I think that's a good starting place for some of this.
I think on this slide you show here, mainly talk about high frequency. This is related to the shared geology. How about low frequency?
So in this study, the lowest frequency was 2 hertz.
But there's no kind of correlation with.
I think there is actually. I just cut this off because it's too many panels. But in this paper, you can see that I think even at 2 hertz particularly for the S, I think there is still correlation with this geology. But I think this I think it's pretty shallow, so we expect it, but the higher frequencies. Yeah.
I think people kind of touched on that a little bit already, but how much do you think the propagation and side terms that people have inferred from the, the dot motions are actually from the near source structure? So, like Yahuda and Alice, they have shown that when you have this near source structure, they kind of factor about them seismic data already. So, how we separate them?
Yeah, so I mean, I think we can. I think this is an example where we can separate them, right? Because these are small events that are occurring primarily outside this array, and we're seeing these repeatable effects. So these are from the fault zone structure and not from, I think the question is from like a main shock rupture on these faults, right? That's where these small magnitude data are really valuable, right? Because we can treat them as point sources with very little source complexity, right? At least at these scales, and see this. I mean, this is a really strong example of this repeatable segment. And then just to hammer this home, I think if you just pick one station in this area, 2 stations, which is what we have normally, right? You wouldn't see any of this. You wouldn't have any idea of how this fault is creating these structures or what we would expect here. So.
Just a quick follow. So what about arrays on the fault versus arrays off the fault if you're trying to see the deep structure of the fault? Because if you're on the fault, it's hard to see through it, maybe.
Yeah, sure. I think probably all arrays. Yes, all arrays are probably great too. Yeah.
Yeah. Okay.
Yeah.